Okay, this is Chemistry 111, experiment number 8, buffers. This is taken from a Vernier buffers lab. The purpose is to make two different buffer solutions, one of which has a huge amount of conjugate base present compared to the first one. They're both going to be weak acid buffers. And we'll find their buffering capacity, that is, how much titrant do you need to change the pH by 2 units in either direction. So we'll make a buffer. We'll set up two burettes, one with acid, one with base, and we'll find out how much base we need to add to raise the pH by 2 units. And we'll find out how much acid is required using the acid in a different burette to lower the pH by 2 units. Note that these are buffers, meaning that they are supposed to be resistant to a change in pH, so we expect it to be a lot, right? But how will it vary with the two different buffer solutions we have, one of which has a huge amount of conjugate base, the other one not so much? All right, so let's do a little review on buffers. They're solutions that resist a change in pH. How do we do such magic? Well, start with a weak acid, like, say, acetic acid, or in this case, nitrous acid. See the H plus there? There's your acid. But it's weak, meaning that it doesn't dissociate much. It normally means it's not as dangerous either. And add a little bit of its conjugate base. This happens to be sodium nitrite. It could as easily be potassium nitrate. The cation doesn't really matter, because when this dissociates, it makes H plus but NO2 minus. So we're adding more NO2 minus in the form of sodium nitrite. You could do the same if you had a weak base, add a little bit of its conjugate acid. Now, important note, we're not doing that for this experiment, but if we were, we could start with some ammonia and add some ammonium chloride. So that would be our weak base. Here's its conjugate acid, ammonium ions, and in this case we had a chloride anion that goes along with it. That it doesn't matter much. And but that's not our experiment, so ignore this stuff. What we'll be doing is making the weak acid. And here's how the weak acids work. You could do analogous stuff for weak bases. If you add some base, they'll resist the base just adding to solution, because you've got, after all, a weak acid present, right? So that weak acid can react with the base, and it'll make some water and some more nitrite ion. That too should be a subscript, but the minus should still be a superscript. So that's nitrite anion. The conjugate base can react with the acid. If you add acid, well, that will get sucked up too, because after all, we have conjugate base that can react with acid. So we've got both acid and base in solution, if you will. Not formally. We do have a formal acid, but we only have the conjugate base. It's good enough because it can react with H plus to form HNO2. And there you go. And that HNO2 is a weak acid, so it will resist a change in pH. The best relevant equation for this is the Henderson-Hasselbalch equation, where the pH of that solution should be equal to the pKa of that solution, depending on what the acid is, and the log of the concentration of the acetate anion over the regular parent acid. In this case, we'll be using acetic acid, and we're giving you the fact that it has a Ka of 1.77 times 10 to the minus fifth. Ka doesn't show up in here, but it's, very easy to do the calculation. Helpful note, 10 to the minus pKa will give you the Ka. So we're going to compare the buffering capacity of two different acetic acid buffers. One has a mungo amount of acetate in it. That's buffer B. The other one doesn't have so much. What will they do? How will they compare? How will the amounts of titrant vary to change the pH by 2 units in either direction, and which one do you expect to be larger than the other, and why? All these things are curious, or we can just start the experiment and see what happens. This is the summary table, which gives you a good idea of what we're up to, right? We're going to need to know the concentration of acetic acid in moles per liter, the concentration of sodium acetate in moles per liter. Since it dissociates into one sodium cation and one acetate anion, it's reasonable to assume that the acetate ion concentration is the same as this. And we'll find out the volume that we need to change it by 2 pH units. That's what we'll do in the procedure. So let's get rolling. We'll be setting up something that looks like this. We'll set up two burettes. Most of these clamps are designed to hold two burettes, so lo and behold, we'll use both sides. We'll have a beaker that contains our stuff we want to titrate, either buffer A or buffer B. And first we'll titrate it with some base, and then we'll titrate it with some acid, and we'll see how much it requires, what giant amount of titrant is needed to change the pH in two directions. Okay, so here's some details. Part 1, titration of acetic acid buffer with base and acid. So we'll make a acetic acid buffer solution by just taking some acetic acid solution, which I believe is already prepared as a fixed molarity concentration. Add a little sodium acetate as they prescribe, and be sure you follow the directions there, and that's it. You got yourself a buffer solution. Set up your two burettes, one with the base, one with the acid. And we have to do the evil calibration step that we did last week, which caused a little bit of confusion, but we got there. If you're curious, that's on step 4 of page 49. So that's where you calibrate it with pH 4 and pH 7. I'm going to assume you can roll through that easier now because you've done it once already. We will then titrate with the base. This is a weak acid, so we should be able to add some base and neutralize it. Open that logger profile, 19 for buffers. Measure the pH of the buffer solution as it is right now. It's a weak acid. And raise it precisely by 2 pH units. That should just say 2 pH units. And we'll find out the volume necessary to do that and the pH that you get to. I guess mathematically that's easy. Now we'll be doing it like we did last time, where you add 0.5 mils each time and record the pH. Notice that you guys found out last time it's a lot of measuring, so you do not need to be ridiculously precise and take 5 minutes for each 0.5 mils added, and we should be able to get it up to pH units. We'll continue to add base in small increments till you've done that, after you've done it, right? So here's a little thing for this. Not sure why we really need to do this. We'll see if it becomes important, but we'll continue to add base in small increments after we've gone up 2 pH units to go past that equivalence point, which was such an exciting moment last week. We'll find the volume of the base that was needed to go up those 2 pH units. They give you some instructions for how to do that precisely. I bet you can just get a very good estimate without it, but follow the instructions that they go through so that we can line up a crosshair with exactly pH 2 units higher, and we'll print that out. Next, let's titrate it with acid. It's supposed to be resistant to pH change in either direction. So repeat trial 1 with some fresh stuff and see how much acid is needed to lower the pH by 2 units. We don't have to print this one out, so you'll use the same procedure and we'll find out how much it takes. In part 2, we're going to make another solution this time. This will be, yes, buffer B, which is the same buffer but with 10 times as much acetate. In this case, it's sodium acetate. So we'll make the same solution with 10 times as much sodium acetate. Do the same thing. That means titrate it with base, find out how much it takes to go up 2 units, and go ahead and go past the equivalence point and find the pH required to get to the volume required to get to the equivalence point. And then titrate it with the acid and see how much acid is required to lower the pH by 2 points. You should understand that if you looked for an equivalence point when you're going down, you will never get there. I hope that makes some sense to you. And then finally, we'll perform our calculations. The experiment's done, clean up, everything goes down the sink after you neutralize it as before, and we'll perform 2 calculations. 1, the molarity of the acetate, that is right there. I believe the molarity of the acetic acid is given. And the theoretical pH of the buffering system, here we are right here, using the Henderson-Hasselbalch equation. And those are the only calculations that we need. Be sure you fill in these. When you write up your conclusions, I'd like to see a little bit of analysis here, right? What happened and why. So I will be looking for that regardless of whether it shows up in these specific instructions. I mean, aren't you curious how buffer A compares to buffer B and why that might be? So please make a note of that. Some handy notes. Don't forget, we always have to record the burettes interpolating between the graduations, which in this case means record things to 2 decimal places, to the nearest hundredth of a mil. And don't forget to condition your burette first. It might have not mentioned it this time because it's assuming you just know to do that. There's lots of beakers, so it's okay to label them if you need to. And please don't forget to answer those post-lab questions. This is the buffer experiment, Chemistry 111.